Welcome back to CS 520. In this session I want to talk about floating point representation. Real numbers often are represented with scientific notation. So this topic may cause you to go back to your high school chemistry class when you probably first were exposed, or at least I was first exposed to scientific notation. Numbers that look like this. Right? Important to keep in mind that these values are not exact. They're approximations of values out there in the real world. For instance, in chemistry class, maybe the first thing you did was you were asked to measure something on a scale, on a balance. And there was obviously some accuracy limit to that balance. And so you recorded a number that was the best approximation you could get to the actual weight of something as limited by the device you were using. In my high school chemistry class, my teacher, Mr. Connard, insisted upon a normalized form. What I'm going to call in this class anyways, a normalized form. I don't remember what he actually said, but he insisted that we write these numbers in some fixed way with one digit, one non-zero digit to the left of the decimal point. Right, he didn't want this when we answered a question on a test. He didn't want this equivalent value. Let's see if I can get this right. I made the number bigger by shifting it to the left, so I need to compensate by making the exponent smaller. He didn't want that number. That was not allowed. And he also didn't want this number, right? If I shift the other way, those are equivalent values, but Mr. Connard insisted on a common response from all the students, probably just to make his life easier when he was grading. But as we'll see, computers are going to do the same thing in just a minute. So once we remember those kind of numbers, I guess another thing I can say is, what were the components here? Obviously there's an exponent up there, a significand here, and this number actually is positive, so we have to remember that there's also potentially a sign, either plus or minus, on the front. Okay. Well, once we remember those kind of values, then there's no reason, as normal with computers, to consider using binary forms of those numbers. So inside the machine, actually, we're going to see there's numbers that look like this. Right? The base is now base 2, and we're restricted to zeros and ones over here in the significand. Usually I'm going to write this exponent in decimal, however, again, a little bit of confusing issue there, but that's probably what I'm going to do. So what is this value? Well, I think that's 1/2, right? Okay, because positionally again now, just like we saw with integers where we had 2 to the 0, 2 to the first, 2 to the second, now we have 2 to the minus 1, 2 to the minus 2. Okay, so we have negative exponents on the base going in that direction. Okay, what's another value? 1.11 times 2 to the 0 is what? It's 1 plus 1/2 plus 1/4. Okay, which I guess is what? 1.75 base 10. And this is 0.5 base 10. Okay. So again, let me just write it down here just to emphasize it. But scientific notation, there's three components. There's the sign, there's a significand, in other words, this part, and there's an exponent. Right, this part, which itself is possibly signed. Actually, I should get rid of the possibly, right? It's signed. It's either plus or minus that exponent. So when we use the term floating point number, what do we mean? Floating point number is computer support for real numbers that uses binary numbers in scientific notation. Okay. In the old days, all computer manufacturers had their own proprietary floating point formats. In fact, many of the vendors still have their proprietary formats, but nowadays the vendors also support a standard floating point. It's known as IEEE floating point. It's actually standard 754, which was established in the mid-80s. And it provides for two basic formats of different lengths, right? There's a 32-bit format, and it allocates the bits to the three components. A sign bit on the top, 8 bits of exponent, and 23 bits of significand for the single precision case. For the double precision case, again, there's a sign bit on the top. Let's see, 11 bits, I guess, for exponent, and 52 bits for the significand. So double precision can support bigger numbers because of the bigger exponent, and also capture more digits of accuracy, more significant digits, just because there's more bits allocated to the significand. Just like my chemistry teacher in high school, IEEE floating point has a normalized form. It insists on a single 1 bit to the left of the radix point. Followed by the rest of the significand times 2 to some exponent. Since this 1 always has to exist, the trick that the IEEE approach uses is that we're not going to store it. We're not going to store that 1 bit because it always has to be there. So we don't need to represent it, so we can actually squeeze an extra bit out for the significand through that trick. But if you think about it, that 1 bit always is present. How do we represent the value 0, floating point 0? As we'll see, they play tricks with the exponent as well. Let's take a look. So the IEEE floating point exponent, it first uses two particular bit patterns for special cases. The first bit pattern is if the exponent is all 0 bits, and there's 2 cases depending on what's in the significand. If the exponent is all 0 bits and the significand is all 0 bits, then in fact the floating point value being represented by the bits is the value 0.0. Okay, so again, exponent all zeros, significand all zeros, then that is the value 0.0. Note it can be signed actually, because the sign bit can be either set or not set in that case. So this really should say plus or minus 0. Okay. However, if the exponent is all 0 bits and the significand is not all 0 bits, then the value is called denormalized. So they actually allow a few denormalized results. They actually are more forgiving than my chemistry teacher was. They actually let us represent a few values, but only a few particular ones that are close to 0, if you think about it. In this case, the exponent is fixed. It's minus 126. You take the significand bits that are present in the number, in the representation of the number, and you put them here, and you assume the leading significand bit to the left of the radix is a 0. So again, with this trick, they squeeze out a few more representable values, and there happen to be values that are close to 0. And that's on either side of 0. Again, I should really have a plus or a minus here, because the sign bit could be either set or not set. So again, the trick here is to allow a few denormalized values and get a few more values that are very close to 0. Okay, so that's one bit pattern where the exponents are all 0 bits. The exponent bits are all 0. The other special case is when the exponent is all 1 bits. And again, there are a couple cases here. The exponent is all 1 bits and the significand is all 0 bits. Then the value being represented is in fact infinity. Infinity might pop up because of a divide by 0, or maybe because of an overflow. And again, this is really plus or minus infinity because the sign bit can either be set or not set. Okay, so exponent all 1 bits, significand all zeros, then the value is infinity. The value being represented is infinity. However, if the exponent is all 1 bits and the significand is not all 0 bits, then the value is what we call a NaN, acronym for not a number. It's an error result basically, so 0 divided by 0 or square root of a negative number would probably be captured with a floating point bit pattern that indicates a NaN. And again, that's exponent all 1s, significand not all 0s. Okay. Alright, so those are the special cases. What about exponents that are not special cases? Well, otherwise, so if the exponent is not all 0s and the exponent is not all 1s, then we have to realize that the IEEE approach uses a biased exponent, which just means that the actual exponent is the stored exponent minus a bias amount. Okay, and for single precision, the bias amount is 127. For double precision, the bias is 1023. So I guess what's missing here is i.e. treat exponent bits as unsigned integer and subtract bias amount to get the actual exponent. Okay, so once we know it's not all, the exponent is not all 0s and the exponent is not all 1s, then we just treat those 8 bits in single precision or 11 bits in double precision as an unsigned int, and we subtract off a constant, either 127 or 1023, depending on whether it's single precision or double precision. That's how we decode the exponent. All right, let's look at some examples. Suppose we want to know what is the floating point representation of that decimal real number, minus 3/4. Let's see if we can code this up. So first thing is I've got to get it into a binary number. And you should be aware that the technique of the algorithm for coming up with the floating point number that best represents an arbitrary real number is a very hard problem, and we're not actually going to tackle that. What's the best approximation to an arbitrary real number? That's a tough question. So on homeworks and tests, I will always give you something that's pretty much an easy value to convert from decimal to binary. Something like sums of powers of 2. So we look at this. What is that? That is minus 1/2 plus 1/4. Right. So what's that? That's minus 0.11. And to get an exponent on this, that's assuming exponent of 0, right? Now that's not in normal form, so I need to get it into normal form before I can actually encode the value. So to normalize that, I've got to shift it left 1 bit position. And since I made the number bigger by shifting left, I've got to compensate by making the exponent smaller. Okay. Now I should be ready to figure out what the exponent is. In this case now, remember the actual exponent is the stored exponent minus 127. 127 because I'm doing single precision, and that's the bias amount for single precision. So the actual exponent now I know is minus 1. So minus 1 is the stored exponent minus 127. So that means the stored exponent is minus, is it minus? Let's see, I'm going to have to add 127 to both sides, so in fact it's positive 126. Okay. Alright, I should be ready to encode the number now. The number was negative, so the sign bit is going to be a 1. The exponent is the next 8 bits. The stored exponent is supposed to be 126. Let's see, I guess I've got to figure out what that is in binary. What's the easy way to do this? Don't know. I know it's 1 less than 127. So that must be that value, because 127 would be 7 1 bits. 1 less than that is just making a 0 in that last position. Okay, so let me use another color here to write the exponent in. So the exponent goes in the next positions. Next 8 positions. Alright, I just copied the stored exponent that I computed 126 in binary over into the next 8 positions. And then the significand needs to come in. The significand now, we have it up here. Remember, there's really, I guess, a bunch of zeros in here, right? And this one does not get stored. So I'm going to copy in the significand bits to the right of the radix point, and that is a 1 bit, and then the rest of the significand is zeros. And I've got to get out to 32 bits, I guess. How am I doing? 1, 2, 3, 4, 5, 6, 7. I need 4 more bits out there. Okay. Now, probably when I ask this kind of question on homeworks and exams and things, I'm going to want you to give me the result in hex. So that means you divide into 4-byte chunks, which I've already sort of done here when I wrote it down. And what do I get? That's a B. That's an F. 4, 0, 0, 0, 0, 0. Okay, so that's the floating point encoding of the decimal value minus 0.75. Again, on a homework or a test, I might say, okay, show that to me in a memory for a little Indian machine. So let's do that over here. Little Indian. Little Indian would put the small byte first, right? So that's 0, 0, and then that's 0, 0, and then that 4, 0, and then that BF. Okay, and Big Indian, obviously, can I squeeze that over here? I guess I can. Big Indian would be the BF first, 4, 0, 0, 0, 0, 0. Again, I'm assuming memory addresses are increasing down the page here. Okay. All right, so that's one example. Let's do one in the other direction. What about, we have X-ray vision, we look into memory, and we see this 32-bit value, which I've represented in hex there. Again, as I said in an early lecture, we look at bits in memory, we have no idea what kind of value is. Somebody has to tell us an interpretation, and so in this case, I'm saying look at those bits and interpret it as a IEEE single precision floating point value. Tell me what that number is in decimal. So now we've got to do a decode. There's really no other way to do this but to go to the bits. So let me write the bits out. 1100 for the C, 0000. A is 1010, then a bunch of zeros. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Again, it's 32 bits, so it's single precision. So I've got to look in here and decode the three components. I know the exponent is those 8 bits right in there. And right off the bat, I can tell that the value is negative. Sign bit is set. What value is that exponent there? The stored value is, that's a 128 on the leftmost end and a 1, so that is the stored exponent is equal to 129. That's not a special case. It's not all zeros, it's not all ones. So now I can subtract the bias amount and get an actual exponent of 2. Okay. So we're pretty much ready to write down the binary form of the number anyways. I got to remember that I have the hidden 1 bit, and then I copy in the significand bits from here to the right. Right? There's the hidden 1 bit that has to be put in, and then there's 0, 1, 0, and then a whole bunch more zeros. And it's times 2 to the second, because I figured out, I subtracted the bias amount from the stored exponent to get the actual exponent. So that's the number. Now I can convert that pretty easily to decimal, actually, because it's an easy case. I can go ahead and make it 101 times 2 to the 0. Right? I can shift the value left, bring the exponent down to 0, and in fact it's a whole number. This is 5.0 base 10, and I got to remember it was negative. Okay. Let's do one with double precision. What if I wanted to represent -5 in double precision? How are we going to do that? Well, we know the sign is going to be 1 bit. What's a significand? Significand is significand is 1 point, again what we just saw basically, right? I start out with that. The number is 5, 4, and a 1, all zeros, times 2 to the 0. So I just have to normalize that number, kind of reverse of what we just did. So it's going to be 2 to the 2nd, right? Now I've got to bias the exponent, but I got to remember I'm doing double precision. So the bias amount is 1023. So again, I have the formula that the actual exponent equals the stored exponent now by the double precision bias amount, which is 1023. In this case, I know the actual exponent needs to be 2, so the stored exponent minus 123, the stored exponent needs to be 1025. Okay, so I can now start to write down the bits, right? I know the sign bit is a 1. I need to come up with what the bits are for this. Well, it's 1024 plus 1, so 1024, 512, 256, 128, 64, 32, 16, 8, 4, 2, 1. 2, 4, 6, 8, 10, 11. Okay, I've got 11. All right, I've got those exponent bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? And then what's the significand? Significand again is I don't represent that 1, so I'm just copying in those bits, 0, 1, and then a whole bunch of zeros out to fill up the 64-bit container. Again, I'll probably ask you for this in hex, so you got to divide this in 4 bits, chunks. And let me put another 0 in here. 0 in there. The rest of those are all going to be zeros out there. So I've got C 0 1 4 0 0 0 0. And in Little Indian format then, that would be 0 0. Well, I stopped short. This is supposed to be double precision, right? I just gave out 32. There's actually going to be a whole bunch more zeros out to the right. It's going to be 16 hex digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I'm going to have to put the Little Indian way over here. Is that on this? Not quite. Let me move it over just a little bit. So Little Indian, I'm going to have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 1, 4, C0, right? 8 bytes, double precision. 1, 2, 3, 4, 5, 6, 7, 8. And big Indian, of course, would be just the reverse of that. C0, 1, 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Well, one other thing we need to talk about, I guess, is the concept of overflow. Like with integers, a value can get too big to fit in a fixed size floating point container. So values are going to overflow in the same way they did with integer values. The question is, think about just for a couple seconds here, is what component of a floating point number actually overflows? So think about that for just a second here. Well, I hope you realized it was the exponent, right? Right, if I only got 8 bits in a single precision floating point, IEEE floating point number, so if the number gets too big, what actually happens is it overflows the exponent category. Again, the significand is just carrying, the digits of accuracy. So when a number overflows, it's actually the exponents is the limit. That probably makes intuitive sense to you, but there's also another thing that happens with floating point numbers and it does not happen with integers. It's called underflow. So floating point values can actually get too close to 0 to be seen. Right? Number gets smaller and smaller and smaller in absolute value, and all of a sudden we can't see it anymore. Sort of the reverse. Overflow is on the opposite of 0, right? The magnitude gets too big to be represented. In this case, the number gets too tiny in magnitude and it vanishes. So the question in this case to think about, what happens to the exponent in this case? And I hope you realize it gets too negative. I don't know if that's actually makes English sense, but it overflows, but overflows in a negative direction, right? The exponent gets too negative. Its magnitude gets too big to fit in the exponent component again. So all of a sudden the number vanishes, so to speak. It gets too small to be seen. Okay, that's the basics of IEEE floating point representation. Let's stop here for now.